1. So let's go through the 113 through 117, the problems that we did not do yesterday. So this is in the yellow book. So I think we took care of everything on page 113. And although let's take a look at problem number 2, make sure we feel comfortable. So you have x, you have f at x, you have 3, negative 19, 5, negative 11, 9, 5, 12, 17. So let's take care of the slope. So what do I have to do from here to here? And that looks like I am adding 8. And what do I do from here to here? I add 2. So my slope is going to be 8 over 2, which is going to be 4. But if you look from here to here, what took place, it looks like I added 16 to that, right? What did I do here? I added 4. Oh, wait, I get 16 over 4, which is also 4. So notice it could change, but the slope stays the same. So from here to here, it looks like I added 12. From here to here, I added 3. So then I get 12 over 3, which is also 4. So notice the slope stays the same regardless of which points I did, as long as it was arithmetic, which is a linear situation. The other problem, we have x and f at x. You got 1, 2, 3, 4, and you got negative 27, negative 23, negative 19, negative 15. So from here to here, that's added 4. From here to here, added 1. So I get 4 over 1. And it's the same here. That's another 4. That's another 4. So we still have a slope of 4. So go ahead and switch the page over to page 114 of the yellow book. And I don't think we did number 4. So we have the graph that kind of looks like this, and they go from here to here. Well, you have this vertical of 1, or looks like that even looks like it's half, right? That looks like it went vertically half, and then it went right 1. So what's my slope? Well, it's the vertical over the horizontal. Well, what's 1/2 over 1? Yeah, it's just 1/2. If I looked at my other graph, it looks like same idea, same graph, where truly this one up 1 and this 1 over 2. So the vertical over the horizontal is 1 over 2. So we have the same slope in that case. It's just kind of how we're counting up. Let's go over to page 115. So we did 5 and 7 yesterday. So let's take a look at number 6. For every hour that passes, the amount of area affected by bacteria doubles. Okay, so bacteria doubles, so that's 2 times. So that's going to be, that has to be exponential, because we're doubling and multiplying. And I would say it's got to be continuous, because it's just going to keep going. So if I had graphed something like this, if I doubled, so way up here, so it kind of looks like that. Okay, number 8 on that same page. The average person takes 10,000 steps in a day. Okay, so a graphical model of this would be, these were all 10,000. Boom, boom, goes like that. So did they just take 10,000 steps, or did they each day take more, steps, 1, 2, 3, 4, 5, 6, all the way to 10,000? So I'd say this has got to be continuous. And I would say that it is linear. And that's all we got. So if we take a look at number 10 on page 116, we didn't do that one. So talked about the Mississippi river, the water flows at the surface at 1.2 miles per hour. So the river flows at 1.2 miles per hour in 1 hour. Okay, so if we graph this in 1 hour, this would be at 1.2. At 2 hours, this is at 2.4, so on and so forth. So that river keeps flowing. This has to be continuous because water keeps flowing. It's linear because it's not increasing, it's just flowing. And if we look down below, we did 11 and 13, but let's look at number 12, where you have the data with the dots that are coming down like this. Right? So it says the math representation state whether the contest is discrete or continuous. This is discrete because we just have dots. And then it looks like it's geometric because it doesn't form a straight line. It's definitely decreasing. And then on page 117, let's see, a lot of these we didn't do. So we have 1x plus 16 equals 36. So subtract 16 from both sides, so x equals 20. Number 16, we have 1 over 6x equals 10. Multiply both sides by 6, so I get x equals 60. Number 15, 425, x equals 850. Divide each side by 425. And if you use the calculator, you're going to get x equals 2. Number 17, we have negative 4 over 7x equals negative 1. So multiply both sides by 7 here. Divide each side by negative 4. And that's going to be 7/4. Number 18, we find the recursive and explicit of each sequence. So I got 1, 2, 3, 4, 20, 16, 12, and 8. So I'm subtracting 4 each time. Okay, so what would my 0 term be then? Yeah, it'd be back up to 24, right? So let's use that. This is arithmetic. So my recursive is going to be next minus 4. My explicit is going to be, because I found the 0 term, we can just get away with using n. So I'm going to say f at n is equal to negative 4 times n, and go with that first term plus 24. Number 19. And 9, 18, 36, 72. Looks like these are doubling, so I'm multiplying by 2. So if I multiply by 2, that's going to be geometric. Okay, so my recursive is going to be next times 2. And my explicit is going to be, well, let's go back this way. Okay, can I find that 0 term? If I multiply by 2, then that'd be 9 over 2. That's that first term. Cool. So now we can use this. That means I can just use n. So I have f at n is equal to that first term, 9 over 2, times our multiplier raised to the n power. And that's all we have. Okay, then number 20. Number 20, we have 6, 7, 8, 9. We have 20, 60, 180, and 540. So this is multiplying by 3 each time. Okay. So my recursive is going to be next times 3. My explicit is going to be, oh, we got to be careful. Friends, this starts with the 6th term. So that means I have to have n minus 6 as part of my equation. Agree? So I'm going to say f at n equals, I don't know because I'm multiplying by 3. So I'm going to go 20 times our common ratio of 3 raised to the n minus 6. Okay, so n minus 6, if I plug 0 in, I get 0. Or if I plug that 6 in, I'd get 6 minus 6 is 0, 0, 3 to the 0 is 1, 20. There's our equation. Then number 21, 4, 5, 6, 7, 10, 20, 30, 40. So we're adding 10 each time. Okay, this starts at the fourth term, so this means I'm going to have n minus 4 as part of my equation. My recursive is going to be next plus 10. My explicit is going to be f at n is equal to 10 times n minus 4 I have to put in there. And then what's that term? Plus 10. There we go. And that's all we had with that. So if you would you change your page over? And we're going to spend 2 days on this lesson. So I won't do the whole lesson today. I just want to get the homework done. All right. So on page 119 in the yellow book, it says the given function y equals 1/4 x. Okay. So what do you think the domain of this would be? Is there any indication it has to be all whole numbers? The answer is no. So we could say that x such that x is all real numbers. I can plug any number in. I could say that my domain could go from negative to positive infinity, something like that. I could plug anything in for x and get a number out. So this is a little different terminology, but that's okay. Okay, another representation of this, well, graph it. Okay, I got a 3 here, 1, 2, 3. Slope of negative 1/4, down 1, right 1, 2, 3, 4. We'd said it'd probably be continuous. And then type of function, the difference or growth factor. So our growth factor, so it's got a common difference, CD, and that's the negative 1/4. So if we made a table of values, we could definitely see some stuff. So we're just trying to rewrite these a little bit. Go ahead and flip the page over. So notice this gave us an actual point, okay? So this is going to mean that it would be discrete, okay? So the domain of the situation has to go along, and they have to be whole numbers. So I'll just write that whole numbers. It starts with 0, so I can go x such that x is greater than or equal to 0. I could say that I could go from 0, hard bracket, to infinity. Those are all ways I could represent the domain. Another representation of this function might be just creating a table. You have n and f at n, where I know that f at 1 is 1, and we could just continue to build upon that. So if f of 1 is 1, then I'm just going to add 2/3 each time. So 1 plus 2/3. And then our third thing would be 1 plus 2/3 plus 2/3, etc. Notice I didn't even work it all the way out. Okay, our growth factor on this is 2/3, adding 2/3 each time. Okay, this is on page 120 at the bottom. So the domain of this is negative and positive numbers. So I could say negative to positive infinity. I could say x such that x is all real or all integers. All integers, or that I that we have for integers. I think that's what we said. Nope, we actually said it z. Okay. Another representation of this problem. Well, it's not going to be the prettiest, But if you had like negative 130 back here, and then this is 57.2 up here, and then this is like negative 124, that's like right here, and this is 54.56, like right here. We can just keep our data going down in some fashion. So let's see, what do we do from here to here? 57.2. 57.2 minus 54.56. So it looks like I minus 2.64. And then 54.56. Did I do it? Hang on, I'm off. 57.2 minus 54.56. 54.56, or a different growth rate. Okay, so this is adding 6 each time. All right, so we start at the 130th term, which is crazy, negative 130th. So any other representation of this function, well, there we go. And what is our growth factor here? Well, I think our growth factor, because we have this, and we plus 6, I'm going to go negative 2.64 over 6. So that's our slope. We can divide that out if we want. Go 2.64 negative divided by 6. So we have a negative 0.44 growth factor. So that would be our common difference on that particular one. A couple more. Let's take a look on page 121. Number 5, the domain of this. Well, it looks like the graph's going forever this way, and it's going forever this way because it's going to keep growing. So our domain, we can say negative to positive infinity. It happens to be continuous. So we could also say that x such that x is all real numbers or something like that. Or you could say that x such that x are real numbers. All of those might work in different ways of representing the domain. Another representation of this problem, I don't know if we can make a table. Maybe we could. Let's see what we do. So we have x, we have f at x, or n, f at n. So it looks like I have a point here which is 0, 1. And then it looks like I have 1, 2 right here. And you can kind of build upon that a little bit. What is the growth factor of this? Okay, so it's growing. This is geometric, right? Okay, because it's not a straight line. So let's figure out what the slope here would kind of be between these and see what's taking place. So it looks like I added 1, but did I also times it by 2? So we found the next one. I bet you we're going to get 2, 4. So we're times it by 2. So our growth factor is times 2. All right, down number 5. Here's our function. This point looks like it's 0, 1. We have another point at 2, 5 right there. So this is continuous because if you look at the graph, it's not dotted. And we're going to do it that. The domain of this, so the domain is going to be x such that x is greater than or equal to 0 because it started right here at 0. Okay. You could also say that it would be, whole numbers, but it's not really whole numbers. It's anything that's greater than 0 or equal to 0. Okay, this particular problem, another way to represent it, well, we have n and f at n. I have 0, 1, and I have 2 and 5, and you can look at the graph, see if you can find any other dots that might work. I think right there is nice. I think this is timesing by 5, and this is adding 2. So I think we have a growth rate of times 5 halves, okay, because you know it's growing. All right. So we're going to stop there, and I'm going to give you something to work on. We'll go over that tomorrow. And this is from the Red Book, the Creek Skills book. If you need a copy, let me know. Well, we're going to do page 43 and 44 in the Red Book, the Creek Skills book, okay? Have a nice day.